Okay, welcome to Wednesday of week 3 of distance learning. Today we're going to talk about density. We're going to talk about density in terms of the concept and how it's relevant to us in chemistry, as well as calculating density when given the mass and volume of a certain amount of matter. So, jumping into density, let's talk about something that we're more familiar with. Let's talk about trees. Here's two lots of trees. The lot on the left and the lot on the right. And if I were to ask you which lot has the greater density, I think most of us intuitively would know that the left side has a greater density of trees. Why? Well, there's more trees. And specifically, it's not that there's more trees, it's that there's more trees in a particular amount of space. Both these lots are the exact same size. But the lot on the right has far fewer trees than the lot on the left. We have 9 trees on the right, and we have many more than that on the left. So we would say that the lot on the left has a greater density than the lot on the right. So this is a greater density than the lot on the right. And we can even talk about this not in terms of trees, but in terms of matter by saying that each one of these is not trees, but instead an atom or molecule. And when we discuss the amount of atoms or molecules in a set amount of space, we can say that this material is more dense than this material. There are more atoms packed in per unit of space than there are on the right. So let's look at another example of density. This is going to be something that went across social media not too long ago. And on the left side, we have a beautiful, perfectly mint stack of $50 bills, which has a certain amount of mass. And then we have that same stack, which has been cleaned in a microwave. And because these are Canadian bills, our money is now made of plastic. And if you put it in the microwave, it does shrink. And so like a shrinky-dink, it reduced its volume. Now, a chemical reaction did take place, but just for our purposes, let's just say that the masses are pretty much the same between the two stacks. The big difference being that this stack takes up way more space than this stack. So which stack of money would be the most dense? Well, this would have the greater density because it's the same amount of mass, just in a smaller amount of space. Whereas this one would have the greater value because unless you can peel all the numbers off all these bills, I think this money is pretty worthless. So now let's shift our conversation from density of familiar things to density of matter. And I want to talk about the different states of matter: solids, liquids, and gas. And the difference between the states is there's more energy within the atoms and molecules, so that's why things tend to change from solids to liquids as we heat them up, because as we heat them up, we're infusing the atoms and molecules with more energy. But as the atoms and molecules get more energy, they also spread out from each other. And as they spread out from each other, they are decreasing their density. So solids are far more dense, or rather the solid of a particular material. So let's say the solid of mercury is far more dense than mercury in its liquid state, which is far more dense than mercury in its gaseous state. So solids are solid, which means they don't take the shape of their container because the atoms are so packed in there. They're so tightly packed that they can't really move around. They don't really have to move. They don't really have the room to move around. But as we go from solid to liquid, we're infusing the atoms and molecules with more energy. Because they're now bouncing off each other with more energy, they tend to spread out a bit. And because there's now space between the atoms, there's a lot more room to move and maneuver. And that's why liquids tend to take the shape of their container, because now the atoms have the space to be able to do that. So liquids are less dense than solids. And then we move into gases. And as things change from a liquid to a gas, the molecules and atoms within the gas speed up and gain quite a bit of energy, and they start bouncing off each other with tremendous amount of force, and they spread out. And as they spread out, the density of gases decreases significantly from the density of a liquid or the density of a solid. And that's why gases tend to float or spread out or disperse in the air. And we're going to learn a little later on next week that the density of a material does affect its propensity to float. So less dense things or less dense materials tend to float on top of more dense materials. And we can take the example of some wood on water. Wood initially will float on water because the wood or the material in the wood is less dense or less densely packed than the atoms within the water itself. And so the wood will float. If we put a basketball on the surface of the water, the basketball is filled with air. The air is a gas. It's not very dense. The molecules are very fall apart, and so it will tend to float on top of the water, which is a liquid and whose atoms or molecules are more densely packed together. Okay, so that's sort of the conceptual aspect of density. Let's now explore the practical aspect of density and calculations. So let's calculate density now, and let's do it in a way that we're more familiar with. When we talk about population, oftentimes we're talking about population density or how many people live within a certain set amount of space. And that's really what density is in a nutshell. Density is how much stuff we have in a certain amount of space. So amount of something in a set amount of space. And it's going to be given as a unit rate. So we like to calculate density as the amount of something per 1 unit of space. So here we're talking about Toronto proper, which is just downtown Toronto, so not the suburbs, but Toronto proper has a population of 2.93 million people. And they all live in an area that's 1,792.99 square kilometers. So let's write down the information that I know. I know the number of people, 230,000 people that live in a space that's 1,792.99, and let's get rid of that 0.99. Let's just round that to make our lives easier. 93 square kilometers. All right, so this is the amount of people here, and this is the amount of space they take up. Now I want to calculate the density, and the density is going to be in the number of people per square kilometer. So let's fill in the information that we know in the equation. Density is equal to the amount of people, which is 2,930,000, and divided by the amount of space they take up, which is 1,793 square kilometers. Okay, now it's just a matter of doing that division. 2,930,000 divided by 1,793. I'm going to get, for density is going to be 1,634.13 rounded people per kilometer squared. So that is my density. That is how many people live per square kilometer in Toronto. And that doesn't mean that if you take a square kilometer in Toronto, there's going to be exactly 1,634 people. It's an average, but on average, there are that many people per square kilometer in the downtown core of Toronto. Now, let's shift gears into chemistry. So now we're going to talk about benzene, which is a molecule. So find the mass of benzene given that it's 250 milliliters of it. So that's going to be the volume. So I'm given volume is equal to 250 milliliters. The density of benzene is 0.8765. So they also give me the density, 0.8765, and they're looking for the mass. So look for the mass, and the mass is probably going to be in grams because the density is in grams per milliliter. So there's 0.8765 grams for every single milliliter of benzene. So for chemistry purposes, density is equal to the mass or the amount of something over the volume, how much space it takes up. Now I'm going to fill in the information I know. I do know the volume. So I'm going to fill in volume here. So volume is, I don't know the mass, I'll just call that M. Over volume is 250 milliliters, and I do know the density is 0.8765 grams per milliliter. And now it's a matter of finding the mass, and I have to isolate M using algebra in order to get there. But that's okay because we all took grade 8 math last year, and most of you took grade 9 math last semester. So we know that if we need to isolate M, our rule is whatever we do to one side, we can do to the other. And in order to eliminate a constant that we don't want, we can do that by doing the opposite operator. And what I mean by that is this M is being divided by 250. If I want to get M all by itself, I have to do the opposite of what's being applied to it. So what's the opposite of dividing by 250? Well, multiplying by 250. If I divide and multiply by the same number, they cancel out. And we can illustrate that just by using some simple numbers. If I go 4 times 3 divided by 3, I'm going to end up back where I started with 4. 4 times 3 is 12. 12 divided by 3 is 4. And so because I divided and multiplied by 3, they canceled each other out. But I can't multiply 250 on the right side without also multiplying 250 on the left side. So I'm going to take 0.8765 and I'm going to multiply it by 250. So 0.8765 times 250, and I get 219.13 rounded, which is equal to, and all that's left on this right side is M. So I know my mass, I've isolated M, and in doing so, I discovered that the mass was 219.13. Let's round that to the nearest gram. So I would write, therefore, the mass of benzene is 219 grams. Let's do one more. This one's going to require a unit conversion, excuse me. So first things first, I'm going to write my density equation. Density is equal to mass over volume. And let's list the things that I know. So 500 grams of sugar. All right, so I have sugar and I know the mass of it. The mass is 500 grams. It occupies a volume. Good. I know volume 2. A volume of 0.315 liters. What is the density of sugar in grams per milliliter? So we're looking for density, and we're looking for density in grams per milliliter. Well, there's a problem. The volume was given in liters, but they want it in milliliters. So we're going to have to convert liters to milliliters before I can start plugging things into my equation. And if we recall our metric conversions, we have the basic unit. So this would be either a meter or a liter or a gram or whatever we're measuring. And then we have the units that are larger on the left and the units that are smaller on the right. So if we're talking about liters, and we're talking about going from liters to milliliters, well, deciliters are 10 times smaller than a liter, or in other words, 0.1 of what a liter is. A centiliter is 100 times smaller from a liter, or what a liter is, so 0.01. A milliliter is 1,000 times smaller than a liter. That means for every 1 liter, if I have 1 liter of something, that would be the same as 10 liters, 10 deciliters of the same thing, which would be the same as 100 centiliters, which would be the same as 1,000 milliliters. So 1 liter is equal to 10 deciliters, which is equal to 100 centiliters, which is equal to 1,000 milliliters. So if I want to go from liters to milliliters, I have to multiply by 1,000. Or the trick that most of you learned was if I want to move 3 spaces to the right on the metric conversion table, I'm going to take the value and I'm going to move the decimal 3 spaces to the right. So if the value is 0.315, 0.315, I take this decimal and I move it 1, 2, 3 units to the right. This is gone, and the value I'm left with is 315. which is the same as multiplying. I could take the 0.35, 0.315, multiply it by 1,000, and I would get 315 milliliters. All right, so we know that the volume is either 0.315 liters or 315 milliliters. Now I have enough information, I can plug it into my equation. We're going to call density, we're just going to call it D, is equal to the mass is 500 grams and the volume is 315 milliliters. Now it's just a matter of doing that division. What is my mass in grams per milliliters? 500 divided by 315 is equal to 1.59 rounded grams per milliliter. We're going to explore density a bit more next week. We're going to talk about comparing relative densities in the gizmo and the module from this week. If you have any questions, please let me know. I will be giving tutorials tomorrow. I'll be online at 1 on Microsoft Teams. I'll post it on the Google Classroom site. Until then, have a great night, guys.